I know that you have a lot of questions, but I want to go over a couple of things because these are questions that you'll come up on the test tomorrow, and I just think that students might face some difficulties. You should be able to do these questions, but I just want to make sure that you're sort of aware. So the first thing is that if I have a vector diagram that looks like this, with two vectors down like this, and this angle I give you, say, is 30 degrees, how would you find the x and y components of that vector? What would the y component be? Like, let's say that this is 2. What would the y component be? Oh, no. No. I know that this is what I'm telling you now. So, like, usually the y component is the sine, right? But here, because the angle is measured from the y-axis, I just want you to recognize that the y component is 2 cosine of 30, and then the x component will be 2 sine of 30. Right, we found this last semester when we were doing 2D forces on the inclined plane, that if you measure the angle from the y-axis, then it switches. Right, so since this is the adjacent side to this triangle right here, then the y component is actually 2 cosine of 30. You'll recognize the problem because you'll see a vector diagram that will you'll see a physical scenario that has a vector diagram that looks like this, where you have 2 equal vectors coming down like this at equal angles. And I want you to make sure that you don't miss the question because you put sine here instead of cosine. Can you do that for me? Make sure this is cosine, even though it's a y component. And the reason is that this angle is measured from the y-axis. It's still the adjacent side, right? Cosine is adjacent over hypotenuse. So the y component is the cosine. And then the other, we've done a lot of these, where is the electric field 0, where is the force 0, those sorts of things. Let me show you a sample problem like you'll have tomorrow in the test. I think it was like 16 or something, 15. Where, wrote this down. Let's say that I have 2 charges, a positive 25 coulomb charge, a minus 1 coulomb charge, and a distance 2 meters away, right here. The electric field, I tell you, is equal to 0. And I want to know, what is this distance? Do you know how you go about that? Let me show you. It's not going to be the same problem, but it'll work out very similarly. And I want you to get it right. So I have 2 electric fields at that point. I'll call this Q1. I'll call this Q2. And try drawing the electric fields. Q1 is going to have an electric field to the right. That's E1. Q2 has E2. I know those have to be equal and opposite. So remember, E is KQ over R squared. In order for these to have the same electric field, this distance here has to be a certain value, the total distance for the 25 coulomb charge. Now, the 25 coulomb charge is 25 times the 1 coulomb charge, right? So what must the distance be? How much more further should it be away in order to give the same electric field? 5 is right. It needs to be 5 times as far away. And so if the 25 coulomb charge is 5 times as far away from the point over here, what is x? The distance between the 1 coulomb charge and this point is 2 meters. What is 5 times 2? 10. So what must x be? Not 10. Don't say 10. The distance from here to here must be 10 meters. So x must equal, let me write it this way. This must be 10 meters. So x has to be 8. Okay? Those are a little bit tricky, so I wanted to show you sort of so that you can inspect them. But get those right now that I've shown you the questions, okay? This one right here, you should be fine. Just remember this whole thing about the cosine sine. Yeah.
With that first one, you do 2 sine of 60.
You could do 2 sine of 60. And in fact, that's what we did last semester is we just took 90 minus the angle. But I think that most of you, because we have this sort of knee-jerk reaction to do our x component, our y component is sine, that you probably would have said just like you said, oh, it's the sine, right? Because that's just sort of what we do. But I just wanted to point that out to you. You are going to get those questions right tomorrow? Okay. Yeah.
Wait, how did you know? How did you get 10?
10. Okay, yeah. So, as you said, actually, that this distance must be 5 times the distance between the other charge. But that distance was 2 meters, and so 5 times 2 meters is equal to 10 meters. The 25 coulomb charge has to be 5 times as far away in order to have the same electric field, because the charge is 25 times as much. So 25 divided by 5 squared is 1, so that gives us the same field. And 5 times that distance is 10 meters. 5 times 2 is 10 meters. Not the same numbers. Maybe even they'll be sort of switched around. I don't remember what it's like, but it's the same idea. So don't just memorize the answer. Okay? What else do y'all want to do today? Any particular requests? That's all that I had on my agenda, but what do y'all want to do? We could do the free response. We've done them, but if you want to do them again, that's fine. Or we could look at old tests. We could look at conceptual stuff. I'm sort of, yeah. We look at old tests, like look at different conceptual questions on the old tests. And if y'all want to come back and look at the free response stuff, we can do so. Okay, you're going to have a question like number 3. Want to look at number 3? Okay, so on these, you just draw the vectors. And there are a couple things that you need to consider is the distance and the magnitudes of the charges. And here I'm looking at forces, so F is equal to KQQ over R squared. And so here, notice that this charge is twice this charge, and this distance is twice this distance. So when I draw that first vector for the minus 4q, I'm going to have twice the charge, twice the distance, so half the force. If I draw my force for that charge in that direction with that size, this one's going to be in that direction with that size. You might be inclined to draw that vector bigger because it's a bigger charge, but it's farther away. And so the farther away impacts the force more. Because they're that way, then the right answer is D. There are lots of different ways to do this. Like I can make the two forces equal, in which case the answer would be C, or I can make the top force bigger, in which case the answer would be B. It's never going to be A or E, at least not in this situation. You'll see one like that tomorrow. There's always one like that. You can see one like this too. We've worked some like these. Y'all want to look at some older exams? I think we've done through most of these. Let's go back and do some older exams. Oh, let's go 15. Really 15 forward. Really any of these. Spring 09 might be a little far back, but most of these are pretty good. You're going to see a 2D force vector problem. Let's see, that's in the free response. But let's look at number 10 anyway. So I want to know what is the force on Q1. And so I have one force that is F2, and then another force that is F3. If I'm clever about it, I can sort of see. Actually, I know what the answer is. Y'all know what the answer is? Let's look. So F is KQQ over R squared. Notice that Q3 is 4 times Q2. And Q3 is twice as far away as Q2. So I can say that my charge is twice what it was. Q3 is twice Q2, and it's twice as far away. So that means that this force is going to be 1/4 what the other force is. So F3 is 1/4 what F2 is. So I'm going to redraw this a little bit differently. F3 is smaller than F2. So can you tell me what the answer is? Look at the answers. What's the only answer that works there? D is right, right? Because it's the only negative answer. And I know that F2 has to be bigger. Now you could go through and calculate F2. And you would say K QQ over R squared. And then you could do the same for F1, making sure that you use 10 to the minus 6 for micro, and getting all your numbers right, and then take the difference between those two. But you're going to find that that force has to be down. Okay, yeah.
The answer sheet says that it's A.
Oh yes. Okay, I'm sorry. Because the force, the charge was actually 4 times as much, right? Q. So this is actually 4 times as much. Y'all see what I did? I made a mistake. So I have a 4 in the numerator and a 4 in the denominator. So those two forces are equal to one another. Sorry about that. So F1 is equal to F2. And if that's the case, then it has to be 0. The point is that sometimes, often, like there's a very obvious question that you might be working a lot, or a very obvious answer rather, that you might be working a lot for the question, but that really the answer, if you sort of think about it a little bit, will become, I hope, apparent to you. Okay? I should get your numbers wrong like I did, and then I get it wrong. Yeah.
So where do you get 1 like happens? So like times 1.
Okay, so imagine that this is F, right? So F on Q2 is K Q Q over R squared. Okay, you with me? And now, how does F3 in comparison? And so now I go through and I say, well, if the force on that third particle, I have 4 times the charge, and I have twice the distance. Because this charge is 4 times this charge, and this distance is twice this distance. So I want to see, how does F3 compare to the force on Q2?
So do you get a 4 on because it's 2 to the second power?
Right. So because it's squared, R is squared, then you multiply that coefficient to R by itself. You get 2 squared. And so these would cancel out with one another.
So if the top number was 9 and your distance was 3 times as far, it'd be the same.
Right. Or if it was 25 and 5 or 36 and 6. Okay? Is that clear? All right. Now holler out if you see anything you want to look at. Look, here's a similar problem to that one with the electric field that I worked earlier. If you came in late, make sure you watch the first 2 minutes of the video, okay? Because I talked about a couple of problems. You want to look at this one? This one's useful. A charge of 2 coulombs is at the origin. What charge then placed at the 2 meter along the positive x-axis? Yeah, what is the value of Q to make the electric field here equal to 0? So E1 is going to be in this direction. I'll call this Q1. E2 has to be in this direction, so I'll call this Q2. And I just want to know, what is that charge Q, Q2, so that these 2 electric field vectors will cancel out. I know that E is KQ over R squared. And I know that these 2 vectors have to be the same. So I have KQ1 over R squared, KQ2 over R squared. I can cancel out my Ks. I could put in some numbers. I have 2 coulombs over 2 meters squared equals Q over 4 meters squared. So that's 32 by 4. Is that right? 32 divided by 4. That's not right. You have this. What did I have for the answer here? A? Oh, 32 divided by 4, that is 8, right? Okay, yeah. So so Q is equal to 32 divided by 4, which is 8 coulombs. And so A would be the right answer. I know it has to be negative too, by the way, because to give me this electric field vector, this has to be a negative charge. Okay? All right. We're okay with your electric field lines. You're going to have to draw them in the free response, and you'll have to, you'll probably have some multiple choice. Where is the magnitude of the electric field largest here? How do we determine the magnitude of the electric field? Go ahead. No, these aren't all the same. Remember with field lines, how do we determine where it's the biggest? Not the distance, but it is a D word, the density of the lines. How close the lines are together. So the point where the lines are closest together, which is B, is where the electric field is the biggest. Remember that? Okay, that's important. Important for you to know how to do that. All right. You're going to have some questions like number 19. You're sitting a certain distance from a point charge and you measure an electric field of E naught. If your distance is halved, what is your new electric field? So I always write the equation, E equals KQ over R squared. I'm halving the distance. If I halve that, is my electric field going to go up or down? It's going to go up, right, by a factor of 4. So D is the right answer. In the concept test that I put on Moodle, there are similar questions to this. We did some in class, but be prepared. You have at least one, I think 2, that are similar to these. There are no, wait a minute, is that true? Oh, never mind. There's kinematics. I think there's just one like where I ask you what is the acceleration. I'm pretty sure that's the case. I'm pretty sure there aren't any velocity or distance. There aren't any velocity or distance problems. You know what I'm talking about? Like this one. Right here, number 16. But there is one where I ask you just what is the acceleration of the particle. That's in the free response. Remember how I was missing a question last time? I only had 7 questions, and there were really supposed to be 8. That 8th question was in the 2D force problem, where you're supposed to find the force. Then I also asked, okay, what is the acceleration of that third particle? But if you know the force, acceleration's easy, right? Acceleration is just F over m. You find the force, you divide by the mass, and then you can get the acceleration. But you don't need your kinematics equations at all for this exam. Okay, anything else on this one? Like this one, for example. That's where you find the acceleration. It's number 12. Number 11 is a good conceptual question. So I have these 3 cubes, and I'm told that cube 3 is positively charged. And, you know, there are really only 2 sets of vectors that I can have. I can have a vector that's in this direction or in that direction, and I can have one that is in this direction or in that direction. And so what 2 sets of vectors, what blue and red vector will give me that net force? they're going to bracket it, right? So it has to be these two. And in order to give me those two, this charge has to be positive, and this charge has, what does charge 1 have to be? It has to be negative. So cube 1 is negative, cube 2 is positive. C. If I double the distance, what happens to the force? If I take two charges and move them twice as far away, the force on one of them due to the other will, what's that word? Will? It's supposed to have another L. That will be, what will happen to the force? Go up or down? It goes down, right? And it's an inverse square. So if I double the distance, it's going to go down by a factor of 4. Y'all can do those, right? I can do those in your sleep, right? Do those in your sleep? Okay, good. Not an easy test, though, okay? Like, this is the hardest test of the semester. Next chapter might be difficult. We have potential on that, but I think that this is probably the hardest. I've never split these two chapters up on an exam. My wife asked me, she's like, we're doing Ohm's Law in lab. I said, we're still on fields and forces. She's like, what have y'all been doing? So she was getting on to me last night. She says we should be farther along, but we're doing just fine. We have some extra time at the end of the semester. Okay, know your conductors and insulators, know how to describe conductors and insulators. Also, conductors, charges move freely. Insulators, they don't move freely. So here, the electrical conductor, best characterizes it. Oh, they're poor heat conductors. The reason they're a poor heat conductor is because charges don't move around very easily. That's how you conduct heat in the same way, is that you have these free electrons that move energy around more readily. So conductors, sorry, it's been a long day. Insulators are poor heat conductors. Conductors are electric charges move freely. Okay? Y'all with me? You weren't with me like a minute ago, right, when I was saying the wrong thing. I've been in meetings all day long. It's been a long, long day. Y'all know how to deal with these, right? If I give you a charge, you can figure out the number of electrons. You would say the charge I give you, 3.8 times 10 to the minus 6, divided by the fundamental unit of charge, 1.6 times 10 to the minus 19. And then that would tell you how many electrons there are. You also do the same when you're trying to figure out which charge is not an allowable charge, because remember, charge is quantized. You can divide by the fundamental unit of charge, and if you come up with a decimal number, then it's not allowed, because you can't have a portion of a charge, portion of an electron or proton. Okay, let's see. We look at some others. You have specific questions for me? All right. It's okay. That was 15. Let's look at 16. I'll holler if you see something.
Wait, that first question, is that?
Yeah. So, I mean, this has to do, we had similar questions on other exams. They were just worded differently, but it's really just conservation of charge. So the up quark has the words make it complicated, but it's really not complicated. The up quark has a charge of plus 2/3 and the down quark of minus 1/3. Which combination makes up a neutron? A neutron is neutral, right? So I can just go through each one. Here, this would be 2/3, 2/3, minus 1/3. Does that equal 0 if I add those up? No. That's probably going to be this one. 2/3, minus 1/3, minus 1/3. That's 0, right? So my up quark and two down quarks give me a neutral charge. That is a neutron. The others, C is minus 1 all told, and D is plus 3 E. So neither of those are correct. Yep.
Can we look at number 7? Spring 18.
Mm-hmm. Okay. So I want to put a third charge here somewhere so that the force on that charge is 0. Oh, number 7. Good, I didn't want to do number 6. Things make me think. I have to really think about them, right? Do you find that you have to think about those? You don't have to think about these. Sorry, man. The test is already printed. It's ready to go.
You can just black out the question.
Yeah, right. Okay, so what is the magnitude of the electric field at point A? I'm pretty sure that you have a question like this. Like you have a question like this in the free response where you have to do all the stuff with the vectors, but I'm pretty sure there's one like this too. This one's a lot easier because the vectors are on axis. I first just draw my vectors. It helps if I draw them to scale. I have one vector in this direction, and then the other vector, so you have twice the charge, that's twice as far away, so it's going to be half the magnitude of it. And then I can calculate the electric field for each of these. Did y'all get how I did that? E is kq over r squared. This charge, oh no, that charge is 4 times what it originally was, but it's twice as far away, so it's going to be the same electric field. Follow that? Yeah? Okay, so now I want to know what is the electric field. Well, now I know that they're equal. I can just do one of them. So I have 9 times 10 to the 9th times 2 times 10 to the minus 9 divided by 2 squared. Cancels, cancels. I'm left with 9 over 2, or 4.5. I can do the same for this up here, but I would find that E is equal to 4.5 because it's twice the charge, 4 times the charge that's twice as far away. To find the magnitude, I say the square root of 4.5 squared plus 4.5 squared. I think that's 6.4, right? I think there was probably a direction question down below this. Can I take this away? Yeah, so what is the direction of the electric field? Well, the direction of the electric field is going to be, I have one electric field there, another here, so it's going to be 45 degrees above the negative x-axis. So let's see if that's an option. Oh, it is. So B is the right answer for that one, for number 8. I try to shy away from those 2-step problems and the multiple choice, but I think there might be one where it's sort of like that, where first you find the magnitude and then you find the direction. But I think,
Like a 4-step.
huh?
This is like a 4-step problem.
Oh yeah, but this was before I did free response. I used to do that more when I had just multiple choice. But now you guys have the great privilege of having, hey, welcome guys. We're glad you're here. They should get half credit, right?
Oh, okay.
Oh, come on. No, you'll get full credit. It's okay. But you should watch the very beginning of the video, okay? Especially the first 5 minutes, right? That was important? You got it? You gonna watch it? Okay. Okay. Any other questions from this exam? I'm going to scroll through. Yeah. Okay, so what is the charge of Q2? Pretty sure there's a question on there. I'm pretty sure I put one. Q1 has a magnitude of 10 coulombs. I know it's positive 10 too, by the way, because the electric field lines are coming out. And then Q2 is going to have a charge that's more or less than Q1. Less, right? It's going to be less because it has fewer lines going into it. So, and it's also going to be negative. So I can get rid of that, and I can get rid of that. I could probably go ahead and guess that it's not going to be B because it's not that much less. But anyway, I count the number of lines: 3, 4, 5, 6, 7, 8. There are 8 lines, and then there are 6 on this other side. So I say 10 divided by 8. I don't know what that is. 1.25, right? 1 2/8, 1 1/4. So it's 1 1/4, and then I multiply that by the number of lines here. So that's 7.5. Yeah, 7.5. Pretty sure you have one very similar to that. Make sure you can do it. Interpret those field lines. Any of these others you want to look at?
$18.
18? Okay. This is conservation of charge. Not meant to be hard. Like once you know how to do it, it's not hard. But you know, that's true for almost everything. Once you know how to do it, it's not hard. So before, I have a charge of -3 coulombs. Since charge is quantized, I still have to have -3 coulombs after, like when we have this interaction and they charge, they transfer charges. So I have +1 plus Q equals -3. So Q is equal to -4. B. Material is a conductor because it's not its protons. Oh, it's none of these. B is right for number 20. Yeah.
Number 19 was talking about the allowable charge. If it's a whole number, will it always be an allowable charge?
Usually, because the way you test is you say 10 times 10 to the -6 divided by 1.6 times 10 to the -19. If I do that, I get 6.25 times 10 to the 13. That's an integer, right? It's a 6, 2, 5 with 11 zeros. So that's an integer. So the key is that the quotient, what's that called? When you divide that number by the fundamental unit of charge, then it has to be an integer value. And that's true for A, that's true for C, that's true for this, but if I divide this number by 1.6 by times 10 to the -19, I get 2.2 over 1.6. I get something that's not an integer. I get 1.4. I can't have 0.4 of an electron or proton. Okay, be clear? So these big charges, it looks like when you do it on your calculator, it looks like a decimal number, but it's not, right? Because it's just a really big integer, and it's expressed in scientific notation on your calculator. Is that clear? This is sort of the most commonly marked wrong answer. Because of that you put it in your calculator, you get a decimal number, but it's not really a decimal, it's an integer. Okay? Yeah? All right. Anything else on this test? We can look at others or any other tests. All right. Yeah.
Like the response, but not the first one. That's
Oh yeah, like the field lines. Sure, there aren't that many really, like that we did in lab that you have to know. That's what you mean, like those things. I know not everybody's in lab, so let's just do them. So if I have two plates, this is easy. We did this. We've done these in class too, actually. If I have two plates, the field lines just go straight across. Right? If I have a plate and a sphere, the field lines, let's say this is positive, this is negative, the field lines go like this. I'll be looking that the lines are drawn in the right direction from positive to negative. If I have one that looks like this, positive, negative, I get an induced charge here. So my field lines go in there, out there like that. What else did y'all have? Oh, you had a dipole, but I've already told you that you're not going to do a dipole, but they would look, we've done these, where they just go like this. Now, they're not going to be the same charge on either side, so they'd look a little different. If I had extra charges over here, then I would have, somehow you could have lines that like sort of come out like this with the right proportion, that they're going to go off into infinity. Likewise, if I had extra charges here, you'd have field lines that will go off into infinity. Likewise, if I had extra charges here, go off into infinity. This one's a little trickier. If I have extra field lines here, it would sort of bend down like that and go away. Okay? The point is that you're going to have extra field lines emanating from the part that has the extra charge, the excess charge. Yeah. Mm-hmm. I'll be looking, yeah, right. But I'll also be looking at the number of lines that you draw. They'll need to be proportional to the excess of charge. So if you have twice the charge, you need twice the number of lines. If you have 3 times the charge, 3 times the number of lines. Okay? And they'll be simple numbers. It's not going to be like 1.3 times the charge. Yeah.
So for like the first one, if you had extra negative charge, where would the...
If you had extra negative charge, I'll do it in a different color. Like let's say you had extra negative charges, then it would look like, not like that, like this. Just the opposite. Okay? And that could be the case. You could have extra negative charge. Does that answer your question? Good. Yeah. Yeah, sure. So I'll do that top one. I hate that the business school, you can't really see the colors on the screen. You can't really see the colors, can you? It all just looks like black and white. All right, so let's say that I have, I don't know, 4Q and minus 2Q. So I would have, say, 1, 2, 3, 4 lines there. But then I'm going to need an extra 4 lines. Because I have twice the charge here, I have to have twice the number of field lines coming out of it. And I have half the charge, so you have half the number of field lines ending, terminating in that negative charge. The number of field lines is proportional to the charge. All right. Y'all do fields and geomatics? Y'all do fields, right? You talk about gravitational fields, right? Yeah. It's important. Okay. What else? Okay. Let's dig in back into, that's back when I used to get 3 exams. Oh, and I didn't even do columns back then. When I didn't care about the Earth. Okay, so this is a Coulomb's law problem, right? Except it's in the context of a thundercloud, where you have this cloud. This is a cloud, y'all. And I have 40 coulombs at the top, minus 40 coulombs at the bottom, and they're separated by a distance of 2 kilometers. So to find that force, I would say 9 times 10 to the 9th times 40 coulombs, divided by 2,000 meters squared. You know what the answer is? Does that not work out to be C? Did you try it?
Yeah.
Okay. I can put in my calculator, but I know it's at least a 3.6. Okay? Look at, these are still good tests to look at, even though they're old. They're still good tests.
Also
Number 6. Okay, this will be, oh no, this would be an okay multiple choice question. It looks complicated right at first, but it's not really, because the electric field, listen, if I'm asking for the electric field at the location where a charge is, does it matter what charge is there? Like this 2 coulomb charge, microcoulomb charge, it doesn't affect the electric field because this is at R equals 0 for that electric field. The only thing that affects the electric field at this location is that other charge. So you can just imagine this charge isn't even there. In fact, I think there might be a second question that follows up to this. Let's see. Yeah, and that's why that 2 microcoulomb charge is there. So let's look at this. I want to know what is the electric field felt by that 2 microcoulomb charge. So I just imagine that I have a positive test charge, not the 2 microcoulomb charge. That charge doesn't matter for the electric field. My imaginary test charge that I keep in my back pocket, I pull it out, and I say, what is the direction of the force felt by that charge? And it's going to be in that direction. So the electric field is up and in that direction, although this doesn't ask for the direction. But the magnitude of that electric field will be kq over r squared, 9 times 10 to the 9th, 4 times 10 to the minus 6, divided by this distance, which is 5 squared. I don't know what the answer is. Do you know?
it says
I'm going to trust that those numbers work out to give me 1,400. Okay? 1,400 newtons per coulomb. But then the next question asks, what is the force felt by that charge? And if I want to know the force felt by this charge right here, that charge sits in an electric field of 1,400 newtons per coulomb. So it's 2 times 10 to the minus 6 coulombs times 1,400 newtons per coulomb. So that'll give me my force. What's that? 2 minus 4. 10 to the minus 4? 10 to the minus 5? What is it? Oh, that was for the angle. But if I wanted to know the force, that's how I would get it. What is that? I think it's 10 to the minus 5. I'm going to put a question mark. Y'all follow what I'm saying on that? Please do, because you'll probably have to do it tomorrow. Let me know if you don't right now. Yes? Right. So if I ask you for the electric field at the position of a charge, the charge that's at that position doesn't matter. Right? There's only one charge that affects the electric field, and that's this charge. But then if I ask you a follow-up question that says, what is the force on that charge? Since you've already found the electric field, it's easy to calculate the force. I just multiply Q times the electric field. And that's in a free response too, right? I've already told you all that in that 1D Coulomb's law problem, I'll ask you, wait, no, is that it? Oh, shoot, I forget. In the first problem, where you have to find the electric field. Did I tell you all that? Yeah. Okay. It's a good question. Thank you for asking that. Yeah.
So what are all the different units for electric field?
Just the newtons per coulomb.
I saw a multiple choice question right asked earlier.
Oh, let's see. Was it on this test?
Yeah.
Okay. Is newtons per coulomb. You know, there is another unit for electric field, volts per meter. Excuse me, but we haven't. I know that we've gotten into chapter 2 where we get into potential, but not for this exam.
I saw another one that I think had like kilograms.
Oh, yeah. So sometimes I'll ask questions that ask what are the basic SI units. And so if you ever want to know the basic SI units, I know that electric field is force per mass. And so that's newtons, or rather, I can break that down into its, not force per mass, force per charge. I can break that down into its more basic quantities, mass times acceleration over charge. That's kilograms, meters per second squared, over coulombs. So those would be the basic SI units. Usually, though, I'm just more concerned about this because I want you to understand that an electric field is a force per unit charge. And I might ask you that in words to describe what is an electric field. And it's based on the force that a charge feels or it experiences. Charges don't feel anything. They're just charges. But the force that it experiences. You can do that, right? Good for me. Okay. What else, folks? Other questions? Is that all? Okay. Don't leave. Give me just a second.